This is Unit 4, Video 10. In this video, we will take a look, we'll use oxidation numbers to analyze chemical reactions, especially single replacement reactions. So here we have a reaction, very simple reaction, magnesium plus hydrochloric acid to give us magnesium chloride and hydrogen gas. This is a single replacement reaction. This is how we've seen this reaction as a single replacement. Essentially, magnesium is replacing hydrogen. Now, if we analyze the oxidation numbers, we'll see that magnesium begins at 0 because it's in its elemental state, and then goes up to a +2 charge because it's in an ionic compound with chlorine being -1. Now, if we analyze hydrogen, we'll see that hydrogen goes from +1, since it's in hydrochloric acid, to 0 because it becomes elemental. Incidentally, chlorine does not change its oxidation number. Chlorine was -1 on the left, it's still -1 on the right. So chlorine here essentially doesn't react. It'll be a spectator ion in this reaction. In this case, magnesium goes up in charge. Remember, we said that going up in charge is actually oxidation, the definition of oxidation. Hydrogen goes down in charge from +1 down to 0, and that is called reduction. Now, anytime you have an oxidation-reduction reaction like this, one substance will be oxidized, another will be reduced. This will always happen. You can't have just one being oxidized, because whoever's oxidized is giving up electrons. Those electrons must go somewhere, and they go to the species being reduced. And that's kind of the idea here. So this is a classical example of an oxidation-reduction reaction. So hopefully you can see now through the eyes of the electrons are actually moving, is what's happening. So here, we always said magnesium replaces hydrogen, but the truth is what's happening is electrons are actually being transferred to hydrogen. This is the key, the heart of what's happening in this reaction. Electrons are being transferred. And this is important because you can actually use these electrons to do work for you. You can conduct electricity. You can, for example, create a battery, and that battery can do work, can power things through this exact reaction. Alright, so let's try to analyze these reactions, tell which element is oxidized and which element is reduced in this equation or reaction. So here we have nitrogen gas plus hydrogen gas to give you NH3. This is ammonia gas. Incidentally, these are not balanced. You can balance the equation. Some of them are not balanced, so it's a little easier to see the reaction itself. Alright, so we have, on the left side, we have zeros for both of these substances because they are elemental. Both nitrogen and hydrogen are in their elemental states. In the compound here, notice that hydrogen is on the right. Now, we said that anytime hydrogen is bonded to a nonmetal, it'll be a +1 charge, if you remember that rule from the oxidation numbers. So here, hydrogen actually has a +1 charge, each hydrogen. Now, you see me put above the charge of each individual hydrogen and below the charge of the total. So obviously the total is +3, and we know that nitrogen then must be -3, and that's the idea. So each nitrogen has actually a charge of -3. Now, that would make sense. Nitrogen is more electronegative than hydrogen, so it would end up getting or attaining electrons, accepting electrons. That's why it's negative. Now, having analyzed their oxidation numbers, we can see, so each hydrogen is a +1, each nitrogen is a -3. So above, I will put the individual charges. So having done this, we see that nitrogen goes from 0 to a -3. Now, it gets reduced, so we call that reduction. So nitrogen is reduced. Hydrogen then goes from 0 up to a +1. We call that oxidation. So hydrogen is oxidized. Now, it's a little unfortunate because the word oxidized is kind of referring to oxygen, but that's actually what oxygen does in most reactions. What it does is it itself grabs the electrons, and as oxygen grabs the electrons, it essentially rips them from the other element, and that's why oxygen will oxidize another element, always taking its electrons away. So that's why we call it oxidation, even though oxygen is not present in this reaction. So that's a little explanation for why it's still called oxidation. All right, hopefully that made sense. The one on the bottom, let me erase a little bit so I can see and make annotations on the reaction here. Let's do the same thing. Let's analyze the oxidation numbers of each of these elements. Now the first one is going to be a bit tricky. Actually, iodine is really easy. So on the right side, you can see that iodine has a -1 charge. So that's pretty simple. You'll see that, rather on the left side, sorry, on the left side, iodine has a -1 charge. On the right side, we can analyze iodine. So here, we'll use oxygen. Each oxygen is a -2. You have 3 of them, so you have a -6 total for the oxygen side. The whole thing, this is iodate, the polyatomic ion iodate. This iodate has a -1 charge. So the question is, what is iodine? So that -6 gives you -1. Oops, this is -1. And that must be +5. So iodine has an oxidation number of +5. You right away see that iodine goes from -1 up to a +5, which is the definition of oxidation. Going up in charge is oxidation. So we can actually say right away that iodine is oxidized. Now, anytime something is oxidized, something else must be reduced. You can probably guess what is reduced. Now, will it be oxygen? Let's see. Oxygen in compounds usually has a -2 charge, and that's exactly what it is here. It's a -2 charge. Since oxygen is present in a compound, it's still in a compound here, and we just used oxygen's -2 charge to determine iodine's charge. So oxygen actually does not get oxidized or reduced. In this case, oxygen is not reduced. Usually oxygen is the one reduced, but it's already reduced here to begin with, so it has to be chromium. And let's show you why chromium is reduced. We'll actually analyze chromium's oxidation number. So on the right side, we can see that chromium has a +3, so that's easy to see. And then let's see what it is on the left side. Now we have to take apart, this is dichromate. We have to take apart dichromate. We'll use oxygen as a -2. Each oxygen is a -2. There are 7 of them, quite a bit. That gives you -14 on the oxygen side. Now dichromate has a charge of -2. So the whole thing must be -2. Now here we have 2 chromiums. The 2 chromiums have to have a charge that, subtracting from 14, gives you -2, and that must be +12. So both chromiums have a +12 charge put together. Now up above, we want the individual charge of every atom. So since we have 2 chromiums, and they have a +12 charge, what's the charge of each chromium? +6, and that's how we get chromium. So chromium goes from a +6 to a +3, and that is the definition of reduction. Chromium actually gets reduced. So we can put this down. Chromium is reduced. Alright, and hopefully these 2 examples make sense. Go ahead and take a minute and try this example on your own. And then let's write an actual balanced molecular and net ionic equation for these types of reactions. Just like we've done with precipitate reactions and acid-base reactions, we can do it with these reactions. So let's do aluminum with hydrobromic acid. Let's write the complete, or rather the molecular equation, the one we used to. So in this case, we got aluminum with hydrobromic acid, which is HBr. This is a simple single replacement reaction. Aluminum will replace hydrogen. We'll get hydrogen being by itself, and then we'll get aluminum bromide. So this is how we've seen the reaction all along. Now remember, we put state symbols to help us write the net ionic equation. So aluminum, being elemental, is a solid. Hydrobromic acid is aqueous. All acids are aqueous. Essentially, remember, if a compound is soluble, it'll be aqueous. In this case, hydrobromic acid is one of the strong acids, so it's definitely soluble. Hydrogen is a gas, and then aluminum bromide, based on solubility rules, should be soluble because bromine is a group 17, which is soluble except for the 3 robbers, so this is aqueous. Okay, and now remember, we break apart anything that is aqueous. So aluminum plus hydrogen gets broken apart with bromine. These 2 are broken apart because they are aqueous. Hydrogen gas here does not get broken apart. And aluminum bromide also gets broken apart. Since it is aqueous, we get aluminum +3, and we get bromide -1. Again, if you want to balance it, you can put a 3 in front if you'd like, if that helps. But this equation doesn't need to be balanced. It's the last one that needs to be balanced, the net ionic equation. Okay, so now we're ready for the net ionic. the net ionic, remember, we cross out anything that stays the same on the left and on the right. And for that, we can see that bromine -1 is the only one that stays the same. So bromine stays the same, we get to cross it out, everything else changes. Now, what you see is that aluminum actually, somebody may say, well, aluminum's by itself on the left, it's by itself on the right. However, aluminum actually got oxidized. And this is the beauty of net ionic equations. You can clearly see that aluminum went from a charge of 0 to a charge of +3. So aluminum actually changes. It gets oxidized. It actually gives up electrons. Who does aluminum give up electrons to? Gives them up to hydrogen. And that's why hydrogen is +1 on the left and then 0 on the right. So when we write the net ionic equation, remember we bring down everything that changes. So we get aluminum plus hydrogen ion, giving you H2 plus aluminum ion. And again, this is the beauty of writing a net ionic equation. You can clearly see aluminum gets oxidized. You can clearly see hydrogen gets reduced. Now, aluminum gets oxidized to a +3 charge, which means we must have 3 hydrogens doing the bidding. And our equation must be balanced. So this one, to balance this one, you can actually, if you put a 3 right here, for example, that won't balance it. Or rather, if you put a 2, here's what I meant to say. If you put a 2 right there, it actually looks like it's balanced. If you decide to put a 2 in front, because you got 2 hydrogens and aluminum. However, the charges are not balanced. You have to make sure the charges are balanced. The easiest way to do this is to actually go back to the original equation, balance the original equation, the molecular equation. So to balance this one, what I would do is I got 3 chlorines, it looks like, 3 bromines. I got 3 bromines, so if I put a 3 in here, I'll end up doubling it to balance the hydrogen. So I'll actually put a 6 in here, a 3 in here, and it looks like I need a 2 in front of here, and a 2 in front of here. So once I've done that, I can actually transfer these same numbers down to the bottom equation, and it will be balanced. So here, if I put a 2 in front of the aluminum, a 6 in front of this hydrogen, a 3 in front of here, and a 2 in front of here, you'll see that the whole thing balances. I got 2 aluminums, I got 6 hydrogens, but now our charge is balanced. You'll see that I have a +6 charge here, and I have a +6 charge here. It turns out that with redox reactions like these, your charge must also be balanced. Alright, if that was a little difficult, we'll do a few of these to practice in class. Go ahead and try one on your own. Try to write a net ionic equation for copper reacting with silver nitrate.